Hello everyone. Welcome to this video, which is part of a series that aims to take electronic circuit concepts and demonstrates them in a practical manner. This video will be taking a look at how to use multimeters to measure voltage and current. And we will do that through looking at series circuits as well as parallel circuits and verifying the characteristics we've learned about them in our previous video. In this video, we will verify the characteristics of parallel circuits with the help of multimeters to measure the current and voltage in a parallel circuit. In the next video, we will do the same, but for series circuits. But first, before diving into these concepts, let's take a look at the tools that we will be using today in the workbench. In this tutorial, we will be using a multimeter, a breadboard, a 9-volt battery, some jumper wires, and 2 resistors of any value you have lying around. The resistor values I'm using in this video are 10 kiloohms and 22 kiloohms. This video considers that the viewer has a basic understanding of nodes, loops, branches, as well as how to use breadboards. If you don't, I've extensively covered these topics in our first video of the series. You can refer to it if you need a refresher. This video also assumes that the viewer is familiar with what series and parallel circuits are. If you aren't, I also encourage you to view the most recent video of the playlist as it concerns series and parallel circuit connections. Multimeters are instruments that can measure electrical current, voltage, and usually resistance. A voltmeter is a device that measures voltage across an electrical component. Therefore, we connect it in parallel to the electrical component we would like to measure voltage for. An ammeter is a device that measures current through an electrical component. Therefore, we connect it in series. Now let's jump to the workbench and look at multimeters. So this is the multimeter that we will be using today. If we would like to use the multimeter to measure voltage, we would need to allocate the quadrant or the part of the multimeter's dial that is related to voltage. We can see that there are two quadrants, or let's say the first quadrant of the multimeter's dials are concerned by measuring voltage. We have a voltage with a dotted line or a straight line, which symbolizes DC voltage, and we have a voltage with a squiggly line on top of it, which symbolizes AC voltage. Now, if we would like to measure current, we would need to turn on the dial to face the second quadrant of the multimeter's dial. The first half of that quadrant is concerned with measuring current in an AC circuit, whereas the second, with the letter A, that has a dotted line or a straight line on top of it, is concerned with measuring DC current. Now, what about the placement of the leads? We have two leads. We have a red and black leads of the multimeter. So how would we connect those leads if we would like to measure voltage? We would always need to connect the black lead to the COM port. And as we've mentioned in our previous videos, the red lead is connected based on the thing that we would like to measure. So since we would like to measure voltage, we would need to connect the red lead of the multimeter to the voltage or to the terminal that has the letter V under. Now, what if we wanted to measure current? For current, we have two placements. We have in the milliamperes and in the amperes. And since I already went ahead and measured the currents through calculations in advance, all the current values that we will be dealing with is in the milliamperes. So we would need to connect the red lead to the milliampere terminal. In this video, we will be taking a look at how we can measure voltage and current in parallel circuits and verify their characteristics. So let's take a refresher on the different types of circuit connections. As we've mentioned in our previous video, components in a circuit can be connected in many ways. Components in a circuit can either be connected in series or in parallel. And these two basic connection methods can then be combined to create more complex series parallel circuits. Series circuits are circuits with components connected in a way where the same current flows through them. And voltage is divided across elements in a series circuit. To calculate the series resistance, we must add up the resistors in series. Parallel circuits, on the other hand, are circuits with components connected in a manner where they share two nodes. Therefore, the same voltage is applied across parallel components. Current, however, is divided at that node. To measure parallel resistance, we use the following equation. In the workbench, we have a simple circuit with two resistors connected in parallel as below. From our last video, we know that current divides and voltage is the same in a parallel circuit. Let's first find the voltage on each resistor and verify with the help of a voltmeter. Remember that voltage for elements connected in parallel is the same. Since the resistors are in parallel with the 9 volts, then all voltages on all resistances are equal. So let's jump to the workbench to measure voltage with the help of a multimeter, starting with measuring the voltage across the power supply, and then taking a look at the voltage across the resistors. To do that, we must place the leads of the multimeter, as displayed, in parallel to the electrical components we would like to measure the voltage across. Now, as we will be measuring the voltage across a 9-volt battery, we should turn the dial of the multimeter to point at 20 volts. This is because 2 volts is too small of a range and 200 volts is too big of a range. So we've got a parallel circuit over here with a voltage connected across two resistors, one that is 22 kilo ohms and the other that is 10 kilo ohms. And so let's start by measuring the voltage of our power supply, which should be supplying 9 volts. So since I'm trying to measure the voltage, I should be connecting my two leads in parallel to the power supply, meaning now this is a whole node and this is another node, right? So I will take my negative or COM port and I'll connect it to the negative terminal. And I'll take the red lead and I'll connect it to the positive terminal. And as I can see, (9.66 volts). As we've seen from the multimeter, the battery supplies about 9.66 volts. Therefore, we expect a reading of 9.66 volts across each resistor. Now, how can I measure the voltage across the resistor? While taking into consideration the polarity of that voltage. Since the power supply is applied with positive ends of the power supply connected to node A and the negative terminal of the power supply connected to node B, we would need to take careful consideration while connecting the leads across the resistor in a manner where we ensure that the positive leads of the multimeter is connected to node A and the negative is connected to the node B. Now, what if I wanted to measure the voltage across this resistor? I would need to take the red wire or the red lead connected to the positive terminal of the or the node that is connected to the positive terminal of the power supply or battery, and take the negative or the black port, the node where the resistor ends. And when I take a look at the multimeter's reading, and I pressed hold because I wanted to make sure that I capture the reading, we can see that we get about 9.66 volts, which is the same as the voltage coming from the power supply. And this is verifying the property of parallel circuits to have the same voltage across parallel components. Similarly, if I would like to measure the voltage across the second resistor, I should get about the same voltage. And I get the same voltage, 9.66 volts. Now that we've verified and measured the voltage across the two resistors as well as the voltage across the power supply, and we verified the property that voltage is the same across parallel elements, let's first try and calculate the currents flowing through the circuit. We have three currents in our circuit. We have the current I that's flowing into node A and two currents flowing out of node A. To calculate the currents, we would need to apply KCL or Kirchhoff current law on node A. When applying KCL, we get the following equation. The current I is equal to the currents IR1 and IR2. Substituting Ohm's law gives us the following equation. I equals VR1, voltage on resistor 1, divided by the value of that resistor, in addition to voltage on resistor 2, on the value of that resistor. And since the voltage across these three elements, the power supply, resistor 1 and resistor 2, are all the same and they all equal 9.66 volts, plugging in that value yields the following results. The current flowing into node A yields 1.05 milliamperes, while the current flowing through resistor 1 is equal to 0.966 milliamperes, and the current flowing through resistor 2 is 0.439 milliamperes. Now, how can we measure the current flowing through an element in a parallel circuit or any circuit? As we've mentioned, we should place the leads of the multimeter in series with the electrical component that we would like to measure the current flowing through. Kindly note, since we calculated the values of currents and we saw that it is less than 2 milliamperes, we can use the 2 milliamperes range to measure the currents flowing through the circuits on the dial of the multimeter. And as we have three currents flowing through node A, let's take a look at how we can connect the multimeter if we would like to measure the current I flowing through node A. We would need to break the circuit as shown and connect the positive ends of the multimeter, or the ammeter in our case, to the positive ends of the power supply and the negative terminals to node A. So let's take a look at how that would look like in our breadboard and the value of current that we get out of using the multimeter to measure the current flowing into node A. So as we can see, we broke the circuit and connected the positive terminal of the power supply to a separate node, and the two resistors are connected together in two separate nodes. And we will take the positive terminal of the multimeter, connect the positive terminal or the red lead to the node where the voltage power supply is connected to, and the negative or the black lead to the node where the two resistors are connected to. And in this way, we have connected the multimeter in series. When we view the multimeter, we can see that the current measured is about 1.406 milliamperes. Now, how can we measure current flowing into resistor 1? To do so, we would need to break the circuit as shown and connect the positive ends of the multimeter to node A and the negative ends of the multimeter to resistor 1, as shown. Now, as we've seen in the previous slide, we must break the circuit in the area where we would like to connect the multimeter in series, and that's exactly what we did. We took the 10 kilo ohms resistor and connected one of its ends to another node. Then we will take the positive leads of the multimeter connected to the node where the power supply is supplying power to, which is node A, and connect the negative or the black leads of the multimeter to the node where the 10K resistor is connected to. And we can see that the value of the current that has been measured is about 9.973 milliamperes. And finally, how can we measure the current flowing through resistor 2? We would need to connect the multimeter in series as shown. We would need to break the circuit at node A, connect the positive ends of the multimeter to resistor 1, or the node that resistor 1 and the voltage source is sharing, and the negative terminal to resistor 2. As we've seen in the previous slide, we changed the node or broke the circuit and changed the node of the 22 kilo ohms to be the node to connect to the node just above it. Then by taking the positive or the red lead of the multimeter and connecting it to node A, and the negative or the black lead of the multimeter to the node above it, we get the following reading, and the current measures up to 0.442 milliamperes. When we compare the values of the actual measurements of currents flowing into node A and into or through resistor 1 and resistor 2 with the expected or calculated, we can see that the results are extremely similar. And there might be a small error. That error can be due to the tolerance of the resistor. It could be to resistances that we have not considered in our calculations. We were able to verify the characteristic of parallel circuits in which current is divided amongst parallel components. Thank you for watching this video. The next video of the series will aim to look at how we can use multimeters and ammeters to verify the characteristics of a series circuit, so stay tuned for that. If you find this channel useful, don't forget to subscribe and like, and leave a comment with any ideas or suggestions on topics you would like me to cover in this series. As always, thank you for watching.